Hello, everyone. Let's discuss axioms of probability. You have a probability, which is a map from sigma algebra to a real line 0, 1. It's a closed set of 0, 1, such that probability of omega is 1. And if you have events A1, A2, which are disjoint, and they all belong to sigma algebra, then the probability of disjoint union of these events is given by sum of individual probabilities. Given these examples, let's take a look at some few more instances and try to understand what these are. Before this, the intuition here is to understand the fact that whenever you have probability of disjoint events, as it is the case in this diagram, it is as if you're computing the area of this object, right? Area that is present here. So the entire thing, the area of the entire thing, and the area of the entire thing, as long as it's disjoint, is the sum total of their individual probabilities. So you can always think of computing probabilities as computing area or volume and things like that, depending on the dimension. And given this, can we take a look at how to figure out what the probability of null set is? Can you compute that value? And the key thing to understand is from the axiom that we have, we know that probability of omega is 1. So we only have two axioms. So probability of previously we looked at axioms of events, and this time it's axioms of probability. So we can rewrite omega as omega union null set. And we know probability of omega is 1. Given this to be the case, probability of omega union phi is 1. So probability of the disjoint, the probability of null set is 0. I think we skipped one step here. So before this, you can write this step. Before writing this as directly as 1, we can write this as sum of probabilities. And since we know this is equal to 1, this is equal to 0. And how do we do that? This is only possible because probability of sigma and probability of, let's say, phi, these are all disjoint sets. So disjoint probability can be written as disjoint union of, let's say, sets can be written as sum of their individual probability, summation of individual probabilities. So that's how you compute this. And if you have something like probability of A complement, how would somebody do this? You can just pause this and think about it for yourself. This can be written as 1 minus probability of A. And then from the second property, you know that A and A complement are disjoint. Because A and A complement are disjoint, the union of A and A complement can be written as sum of individual probabilities. As a result, this is known to be equivalent to probability of omega, which is equivalent to 1. From that, you can compute, depending on what the value of A and A complement is, you can eventually find the value. Okay, what about a scenario wherein you have a sequence of events? A1 is contained in A2, A2 is contained in A3, and these are represented by diagrams like this. Given this to be the case, can you say what probability of, first of all, you have to figure out, are they disjoint? Can we find out disjoint union and disjoint intersection? That's the idea, right? From the axioms, we learned that if you have disjoint sets, if you have disjoint union of sets, you can write it as sum of individual probabilities. Now, yeah, are they disjoint? And not really. So we have to make them disjoint. But I mean, this is a good exercise for somebody to think about. This is A1, probability of A1. What about this one, second one? This as limit as n tends to infinity. This is probability of the nth event. Okay, you can think about as to why that is the case. Now, what if the opposite sequence is given, where A1 is the superset of A2, A2 is the superset of A3? So again, find out the disjoint sets, and use the property that disjoint union of probabilities can be written as in some summation of individual probabilities. So intersection term, you can pause this and think about as to how this would be. This is the opposite of what we had previously. In this case, this one would have the limit term, and this would be the A1. The union is be the A1 term. Okay, so what do we have next? So given this to be the case, we can take a look at a very interesting and an important lemma called union bound. In the sense, for any sequence of events A1, A2 that belong to sigma algebra F, the probability of disjoint union of events is, I won't say disjoint union. This is not disjoint union. It's not specified, right? So probability of all union of events is upper bounded by a sum of individual probabilities. Okay. In the previous case, we looked at cases wherein if it was disjoint, how do we handle it? Okay. Is there a way to prove this? Is there a way to prove this? How do we prove it? First take a look at, consider events A1 and A2. So we know from probability of union, which this should be quite familiar to everyone. This can be written as, and we assume that this intersection term is positive, right? Given this to be the case, you can clearly write it like this: probability A1 union A2 is upper bounded by sum of individual probabilities. Given this to be the case, so we proved this for two events, two sets. Now by induction, so by induction, the result that was valid for two sets or two events is valid for m events as well, for all m. Now, given this to be the case, you can take the limit. Think of these two as, let's say, A1 and A2 union AM plus 1. So given this to be the case, this is more like VM is a subset of VM plus 1. If that is true, then you can take the limit, which eventually, because we take the limit, this is probability. Now you can extend that to infinity. You see what has happened, right? So probability as n tends to infinity, you can, even if it is this solution is valid, even if it is for n infinity terms. Okay, so this is what is called union bound, and we use this often. So you can think of scenarios as to where we use this. Certain events are written as unions, but computing the probability of union is usually difficult, right? You can think of various examples, and computing the individual probability is easy. So any scenario wherein you're estimating some union of events, think of it as, think of an example like error. You want to estimate the error in a given mechanism or phenomenon. And probability of that error is typically union of several events, several sets. But those events need not be disjoint. Because if it is disjoint, you can say disjoint union is equal to individual probabilities, and you directly get the result from the second axiom. But they need not always be disjoint, and you don't know that. As a result, it becomes hard to compute probability of error. But you can upper bound it by the sum, which is the worst case scenario. So, let's suppose you have to do, you're doing, this is the probability of error, right? That you want to estimate. You don't know whether this is disjoint or not disjoint. So you can upper bound that probability of error with sum of all probabilities, which is the worst case scenario. So because you can at least upper bound it with sum of individual probabilities, it will be the extreme end of the error that you are trying to estimate. But at least that's the one thing that you can compute with some mechanism. Otherwise, there is no other way to say for sure as to, or you have to assume that these sets are disjoint, which you cannot make. You cannot make that assumption. So I think one of the important things to understand when talking about machine learning and artificial intelligence is the idea that all problems in the world are problems, meaning scientific or engineering problems, can be talked about in terms of being function approximation problems, right? So the idea of problems being approximations of functions. So function is a map from two elements, and you know there is an input and there is an output, and you want to find an efficient map which maps between the two. If you're able to find a map, then you can do a lot of interesting things like prediction and thereabouts, right? So the way function is defined is function is a map between two sets, domain and range, right? And as I've defined it here, function is a map between two sets. So if you take an example of a function f of x is equal to x square, it's a mapping from R to R2. So as long as there is a mapping between, let's say, two sets, you're dealing with function, and your ability to predict these functions or approximate these functions solves lots of the problems. An interesting book to refer in this field is Halmos's function approximation problems. I think we can probably put up a reference at some point as to where that is. It was a book written in the 1960s. And Halmos is one of the, I think if I'm not wrong, he studied under von Neumann. He solved some interesting problems. So you can take a look at that. And he has written an entire book wherein he describes a bunch of problems and he solves them. And he talks about why approximating functions solves a lot of interesting problems across domains. So I'll give that reference. So given that to be the case, function approximation is an important thing. So these are all examples. Function, modulus x is another function. X transpose x, x transpose is, these are two vectors. You're transposing one with the other. It will give you a real number at the end. You're mapping from domain to range. Range is domain. You take an element of domain and you map it to some d-dimensional real space. The d-dimensional real space, so let's suppose in this particular case, the two-dimensional Euclidean space. So you're mapping the element of the domain to point in the range space. Okay. So this is what constitutes a function. So suppose A and B denote a domain and range sets of a function. Given pairs of elements xi, yi, such that I goes from 1 to n, such that xi belongs to a domain and yi belongs to range, find the underlying function, right? For example, in this particular case, it can be force is equal to mass into acceleration. Even here, this is a function approximation problem. So this acceleration can be written in terms of second order differential equation. So when you're flying planes or whatever, so you're solving differential equations, which makes the design of airplanes and lots of, let's say, devices that you see on a daily basis. So if you look at another example, wherein E is equal to half mv squared, this is also a function approximation problem. So function approximation problem is the precursor for prediction, and we are interested in the business of prediction. So prediction is important to us. So find an element in the range space corresponding to any element in the domain. I mean, this might seem redundant for some of you. I'm taking some of the elementary approaches so that people can relate some of the tools that we're developing or some tools that we're teaching to a lay person or a general student who is not taken these courses. So some of the things that I'll do in this class might seem a little elementary, so bear with me. In some cases, mapping cannot be found, right? And this mapping between domain to range, between two sets of input and output cannot be found. That's why you need new tools, right? For example, you're taking a document, and from that document, you're reading it and you're trying to figure out the emotion of the document, whether it's morose, anxious, accelerating. You're taking a element from a matrix. You're taking an element from the matrix, and the dimension of the matrix is d cross k, and then you're mapping it to, let's say, some set. And can be 0, 1, 2. So this is also a function approximation problem. Let's suppose you take a speech signal and you're trying to map it to phonemes. Phonemes are different sounds. There are 26 alphabets. There are 42 phonemes. Now, and these are a representation of these sounds that you make. Even there, these are all examples wherein the prediction problem is much harder because the range set is non-measurable. This is something that you can refer to my previous sessions wherein I dealt with what was uncountable set and what problems uncountable set problem poses for defining probability on that space, or defining function in general and probability specifically in our scope of inquiry. Attempts were made to learn such functions, right? Different attempts were made over a period of time to develop new tools so that such things were possible. So probabilistic tools, which I've already introduced and you had some taste as to what that entails, can help in mapping domains to ranges which possess uncertainties. The key thing about probability is its ability to have uncertainty as part of the structure, and from that, because uncertainty is part of the structure, it is able to handle uncertainty by using some of the tools, right? Kenneth Arrow once said, whenever you have uncertainty, what do? You take samples, meaning you take some data and you draw some inference from it. That's the whole idea of this entire inference theory. That's the whole idea of inference theory, which is the underlying ingredient for machine learning and AI tools. Not the only ingredient, but one of the dominant ingredient. So what I'm saying here is, handling uncertainty makes learning of functions more feasible. Now you can instantiate, again, we have defined these, but we will define this a little more carefully. And every time you talking about something called a random variable, we have previously seen, I'll define this carefully. Okay, it's there in a couple of slides, but random variable, it's neither random nor is it a variable. It's a deterministic function which maps sample space, which is a collection of all outcomes, exhaustive collection of all outcomes, and it maps the sample space to a real number. Okay, this is something that you've seen already. This is omega, capital Omega, which is a set of all outcomes. For example, and underlying all this is a random experiment or a random trial. Okay, so you have an experiment, which is the event, and that experiment has outcomes. The event has outcomes. The trial has outcomes. And the sum total, this exhaustive set of all those outcomes is there in the omega, the capital Omega here, which is the set of all outcomes. And for example, if tossing a coin, the exhaustive set is head and tail. And if it is the experiment is throwing a 6-faced die, it can be n-faced die as well. If you throw a 6-faced die, the set of all outcomes is 1 to 6. Thank you.